Hi Year 11, welcome to Term 2. So this term we are going to be looking at derivatives and calculus, which may seem like a difficult topic to start with and to be doing online, but it's a lot of processes and rules, so it's actually quite a good one to do. The hardest bit of this topic, I think, is this lesson, which is the limits. I find that's probably the hardest thing to get your brain around. But limit questions don't come up too often in the IB exams. They're there every so often, but once you have it and you understand it, you'll be fine. So with limits describe the output of a function as the input approaches a certain value. And we write this in this type of notation. So we have LIM. Underneath that we write x and an arrow, and then we'll have a value of the function, and that equals L, which is also a value. So we say this as the limit as x approaches a of the function f of x becomes close to a fixed value L. So with this, it's looking at what y value the function is approaching as it gets closer and closer towards an x value. And if the function does not become close to a fixed value, we say the limit does not exist. A nice lovely Mean Girls reference for you there. And functions are convergent if the function approaches a fixed value, otherwise we say they are divergent. And we've got two little examples here just to kind of show convergent and divergent. So with this first one, we can see it's going 0.3, 0.33, 0.333, and then that next one should actually have an extra 3 on there. And we say that this one is convergent as each time you can see the number is getting closer towards a third, which is 0.3 recurring. So because it's getting closer and closer to that value, we say it's converging. Now if we look at B, we have 2, 4, 6, 8. If we carried this on, it would carry on going forever until it reached infinity, which doesn't exist, which means it's divergent as it's not approaching a set fixed value. So our first example, we're going to use a graphics calculator to examine each function and find the limit. So the first one we have the limit as x approaches 2 of x squared, and for B we're going to be looking at the limit as x approaches 3 of x squared minus 9 over x minus 3. Now I've already plotted these on a graphics calculator and inputted them here for you to see. So with limits, what we want to look at is when x is approaching the value of 2, from the left-hand side of the function and the right-hand side of the function, what y value is that approaching? So I've plotted the point where x equals 2 on the graph here, so you can see that already. Then I'm just going to draw an arrow from the right-hand side and from the left-hand side. Now I want to see from each of these sides, what y value is that function getting closer and closer to? So as you can see there, it's approaching the y value of 4, which means our limit as x approaches 2 of x squared is equal to 4. So that's how a limit works. We just look at either side of the equation, look at what value, if we come from either side, are we getting closer and closer to, and in this case it is 4. So the limit as x approaches 2 of x squared equals 4. Now for part B, we want the limit as x approaches 3 of x squared minus 9 over x minus 3. So you see here, I tried to plot the point of when x equals 3, and I got that it is undefined. And that's fine, because with this function, if you look at our denominator, it is possible for it to equal 0, and that will be when x equals 3. And when x equals 3, it means that this function doesn't have a solution, as we can't divide by 0. But in terms of limits, it will still be approaching a fixed value. So if we look at, from either side of this function, what y value it's approaching, so if we look from the left-hand side and the right-hand side, and if we were to look at those values, they will be getting closer and closer towards the y value of 6, which means the limit as x approaches 3 of x squared minus 9 over x minus 3 equals 6. And now for part C, we have the limit as x approaches 0 of the function, where the function equals a piecewise function, and it's 1 for x is greater than or equal to 0, and -1 for x is less than 0. So I've graphed that here for you, and as you can see, when a function is equal to 1 or negative 1, it's just a horizontal line. And the 1 has the coloured in circle at the start because it's equal to that. And the negative 1 has an open circle because it's only less than that value. So thinking back to grade 10 sets there. Now we want the function as x is approaching 0 from both the left and right. So if we draw an arrow on this one towards the y-axis and the other way as well, you'll see that they're both approaching the y-axis, but they're not approaching a fixed value. So the black line is approaching when y equals 1, and the purple line is approaching when y equals negative 1. So as they are approaching different y values, the limit does not exist. This is an example of how that works. It has to be approaching the same y value from both directions. And when writing the solution to this, we literally just need to write that the limit does not exist. We also have limits at infinity. So a function has a limit as x approaches infinity or as x approaches negative infinity if the function is either a constant or if it approaches a constant value, such as the horizontal asymptote. So what you will find is that limits link very closely to your horizontal asymptote, and we're going to see that in the next example. So in this example, we are going to discuss the behaviour of the function 2 minus x over 1 plus x near its asymptotes and deduce their equations, and then if they exist, state the values of the limit as x approaches a negative infinity of the function and the limit as x approaches infinity of the function. So the first thing we're going to be doing here is actually deciding where the asymptotes are of the equation. So remember, we're going to have a vertical asymptote and a horizontal asymptote. Now the vertical asymptote, remember, we find by making the denominator equal 0. If we do that, you'll see that x is going to equal negative 1, and that will be our vertical asymptote. Remember, asymptotes have to be x equals or y equals. Now with the horizontal asymptote, we look at the x's on the numerator and the denominator, and we divide the values in front of the x's to get our horizontal asymptote. So in front of the x on the numerator, we have negative 1, and that will be divided by the number in front of the x on the denominator, which will just be 1. And then negative 1 divided by 1 equals negative 1. So the horizontal asymptote is at y equals negative 1. Now I plotted a graph on my GDC of this function so you can see where the asymptotes are, and it will help us with part B of this question. The vertical asymptote of this function was at x equals negative 1. So you see here, I'm just going to draw a dotted line at negative 1, x equals negative 1, and you can see that the green function is approaching that value. And then the horizontal asymptote was also at negative 1. So in pink here, I'm just going to draw a dotted line across at when y equals negative 1, and you can see that the function, the green graph, is approaching that pink dotted line horizontally. So for part B, because there are asymptotes, it means that there are limits, and we only need to look at the horizontal asymptote. So as x approaches a negative infinity, it's going this way, the value of y will be approaching negative 1. So the function is getting closer and closer to the value of negative 1. That's why there's an asymptote. So we can say that the limit as x approaches negative infinity of the function equals negative 1. And that's what you'll find with these questions. The asymptote is also the limit. Now we'll look at the other way. So as x approaches infinity, the same thing's happening. As it approaches infinity, the asymptote is once again at negative 1, which means the limit as x approaches infinity also equals negative 1. Once again, the horizontal asymptote of this function. So this last little bit is on limits of sequences. So when we have an infinite geometric series where the ratio or the absolute value of the ratio is less than 1, so that means the ratio is between negative 1 and 1, the series converges to its sum. Therefore, a limit exists, and that is our sum to infinity formula. So remember, with infinite geometric sequences, the value of the sum approaches a set value. And if the absolute value of the ratio is greater than 1, So basically 1 to infinity or -1 to -infinity, then the series diverges and it does not have a limit because it will carry on getting bigger and bigger and bigger and it doesn't approach an end point. So our sequences and series actually links quite well to limits, especially with our infinite geometric sequences. So once again, the sum to infinity is actually a limit as it's approaching a set value. Now, that's the end of this video, so you can go off and do from your booklets page 1 and 2. If you have any questions or problems, please just send me an email and we can work out what's going wrong, or I can explain things in a bit more detail if you need that as well. Have a great week and I'll talk to you soon.